So we'll be speaking about or discussing about the hardware and mechanics of 3D printer predominantly. Uh, this like since I've already introduced myself, these are a couple of projects that I did back in college days. College projects, keep that in mind, please. Not so good or in in par with the quality of industrial products or anything like that. So, like I've told, building products or building things has always been my passion, and 3D printing has been one of the integral part for that. So, moving on to our topic, 3D printer can be the hardware of 3D printer can be divided into three main parts: mechanics, electronics, and software. We'll be predominantly dealing with the mechanics and some aspects of electronics too. We won't be touching the software part because it's out of my expertise, and it's a very complex area, to be frank. Uh, uh, Before moving to the hardware side or the parts of the 3D printer, I would like to give a quick explanation or quick description of how 3D printing works. Um, 3D printing basically takes or the entire process involves in the first step we take a 3D model and splice it up to different layers, 2D layers, and we use plastic or some sort of material deposition technique to deposit the layers either in lines or maybe a layer entirely at a time in case of um, uh, laser sintering and stuff. So as you can see, a tooltip moves and deposits fused plastic material in its path, and layer by layer, it builds a 3D model or 3D object. That's how 3D printing works. So uh, that is the basic principle or the basic working method of a 3D printer. In order to achieve that kind of a motion for the tooltip, the 3D printing tooltip, we need to have or we need to define or we need to establish the kinematics. Kinematics simply means deals with the movement of the tooltip. It can be either the Cartesian in delta, polar, or Scara method model. I hope you are all from a mechanical background and you will be able to grasp these things: Cartesian, delta, polar, and Scara. They are simply different kinds of motion. Okay, I'll be showing videos or how they work. So if you are not understanding, you can unmute yourself and ask question. I'll be quickly clearing the doubts if any doubts are there. This Cartesian kinematics is predominant in the 3D printing industry. Cartesian kinematics has a major share. Most of the 3D printers are built based on Cartesian kinematics. There are two types of 3D printers based on Cartesian method or Cartesian type: core XY and moving bed type. I'll be speaking in detail after saying about delta and other stuff. We'll be seeing videos of core XY and moving bed works, but first let me complete the delta and type all stuff. So in case of delta, you have three control inputs, and based on three control inputs translation, we get the movement of tooltip in a 3D space. You can see how it works here. There are three drivers or motors located on the bottom panel here, and it drives these links, 6 links, and based on the height of this links, you can literally decide where the tooltip is or where the tooltip needs to be, and you can drive the motor to achieve that kind of a motion. See. It has a motion in a 2D XY plane or a 2D layer, and it has a translation motion in the Z direction, and that's what helps us to build 3D object using delta method. Okay, moving on to the polar type. Polar type has in previous case delta, there were three translation motions, and these three translation motions was translated into or converted into 2D and 3D motions. In polar case, in the case of polar 3D printers, we have two translation motions, one in the Z direction, one in the X direction, and the other one is rotational motion. The bed rotates. You can see that in the following video. So you can see the bed rotates and moves in the Y direction or X direction. It depends on how you define the motion. But the fundamental thing is that you have a rotating and translating bed, and in the Z direction too, you have option to adjust height and print accordingly. So that is how a polar 3D printer works. Okay, now the other one is Scala. These things are usually found in industrial testing robots because they are very fast and they have very accurate work envelope. Uh, they can achieve their motion targets very fast and accurately. Here in this video, you can see everything except the Z direction is angular motion, right? You have one pivot here or joint here and another joint here. We may call it as X and Y, and the height or translation motion as Z1. So in the X joint, it rotates, and in Y joint, it rotates. And combining those both rotations, we get our desired motion, right? Okay. Let's explore further into the Cartesian type manipulation of tooltip. Uh, the advantages of Cartesian type is that it's simpler to build. It has a simpler mechanism. The calculations or the kinematics, reverse kinematics, etc. I hope you are familiar with those things. In order to achieve a particular motion, we have less complex calculations in case of Cartesian, and it is very compact. Yet you have large build volume in case of Cartesian 3D printers. Okay, types of Cartesian 3D printers. There are several types of Cartesian 3D printers, like I have told, core XY, moving bed, and other sort of things. But before moving to that, let's see how a Cartesian type works. We have a tooltip here. It moves in an X direction, and a gantry moves in the Y direction. And we have a bed here that moves in Z direction, up and down. In core XY, this is a video of a core XY 3D printer in action. You have a tooltip moving in X and Y direction, basically in a 2D plane, and the bed moves down to build volume in the Z direction. Yes, so that is how a core XY 3D printer works. Notice the bed is what is moving in this case. Now coming to moving bed type, in previous case, the bed moved in Z direction, up and down. In this case, the bed will be moving in Y direction. A tooltip will be moving in X direction only, and the entire gantry will be moving up and down. In the former case, it was the bed that was moving up and down. In this case, the tooltip is moving up and down. Okay, as you can see, the bed moves in the Y direction, the tooltip moves in the X direction, and the entire gantry moves up and down in the Z direction. See, X direction and Y direction, bed moves in the Y direction, and the entire gantry or the carriage moves up and down in the Z direction. Let's see one more close-up working of that instead of a time-lapse one. We spoke about a moving bed type, a moving tooltip type. Now let's see what uh, this special kind of 3D printer is doing. In this case, the entire X and Y carriages move upwards. The bed is stationary. Bed is not moving at all. It's stationary, completely stationary. What moves is the tooltip moves on X carriage. The X carriage moves on another carriage in the Y direction, and the entire X and Y carriages move upwards in the Z direction. So that is how this racing carriage type 3D printers work. These kind of things are especially used for building extremely large volume objects which are not conventionally built on small printers. This is kind of an industrial model. It's not usually found with household or hobby 3D printers. There are 3D printing experts who work on such kind of printers that are predominantly made by themselves, not bought from market. So this is a custom built 3D printer. Okay, before moving on to the next section, if anyone has got any doubts, you can unmute yourself or maybe raise the hand and ask the question. I'll be clearing the doubts and moving to the next section.
Yeah, participants can ask questions if you have any clarification required. I think Adil, you can continue.
Okay, so before moving on, uh, let me quickly recap everything. Uh, we have different types of kinematics: Cartesian, delta, polar, and scalar type of kinematics. The predominant one or the biggest or the most used one is Cartesian type. We have two different types: core XY and moving bed type in the Cartesian type of kinematics. The delta, three translation motions are used in the up and down direction to achieve the 3D motion. Uh, in case of polar, you have two translation motions, one in the Z and one in the X direction. And the bed rotates, the entire bed rotates. Uh, and in scalar type, you have two rotation motions and one translation motions. In two rotations, here, here, and translation motion, the entire arms move up and down. Uh, Cartesian types are simpler mechanisms. Less complex calculations are required. Only less complex calculations are required to achieve motions, and it is compact yet large build volumes can be achieved. And in types of 3D printer mechanisms, we have core XY, in which tooltip or the head moves in the X and Y direction. The bed moves downwards to build volume. And in moving bed type, we have the 3D printer that has a moving bed, that the bed moves in the Y direction, tooltip moves in the X direction, and the entire carriage of tooltip moves in the Z direction to build volume. In this kind of racing carriage type, the bed is entirely stationary. The bed is entirely stationary. We have X direction, X motion, Y motion, and the entire carriages are lifted up in the Z direction. Okay, so moving to mechanical parts, we have seen a couple of 3D printers. The fundamental or the basic building block of a 3D printer is its frame. It can be achieved by it can be built by using sheets of a certain kind of thickness and joining them like a jigsaw puzzle or something like that, or it can be built using aluminum profiles or square pipes or things like that, or it can be a combination of both. But while building a 3D printer, what we have to keep in mind is that everything has to be very rigid. It should not be flimsy, and uh, everything has to be built in a strong way, and everything has to be parallel. we'll speak about paralleling afterwards. Okay, so here we have a bed, moving bed type. The bed moves on a couple of rails or rods, as we call it, steel SS rods, linear rods, and these linear rods are implemented in order to achieve smoother motion and ensuring parallelity, or sorry, not parallelity, sorry, perpendicularity between the moving arms and carriages. So this one is a linear rail. It is an expensive one. It is very good if you want a very accurate 3D printer. These kind of things like a roller type, a V-groove roller type things are used in lower value 3D printers because it's cheap to build and cheap to maintain. So these kind of things can be found in most of the 3D printers. Then these are timing belts, GT2 pulleys and timing belts, which are used to drive these carriages and tooltips and stuff. This bearing is a special type of bearing. It's called a linear bearing. Unlike rotation or rotary bearings, these bearings are built to predominantly support smooth linear motions. These are locking nuts and these are threaded rods. Threaded rods are usually found in the Z direction because in the Z direction we need good rigidity and good accuracy. If we use a timing belt or a rubber belt, there is a chance that it stretches over time and we will not be able to achieve good precision in the Z direction. So we use threaded rods in the Z direction. There are 3D printers which use threaded rods in the Y and X direction, but predominantly since Z direction motion is compared to X and Y direction slow, we use 3D GT2 belts in X and Y direction and threaded rods in the Z direction. Okay, so we spoke about locking nuts or anti-backlash nuts. Sorry, not locking nuts, anti-backlash nuts. Anti-backlash nuts are an important part of a 3D printer because 3D printers basically works in micron level. So if you have noticed, in case of a nut and bolt, you can see a small plate, a back and forth motion, even if you completely thread a nut onto a bolt. So in order to avoid that, we use two separate nuts and they are loaded by a spring. So this portion of the nut presses against this portion of the thread and likewise in the opposite direction. So usually this is the play gap or the allowances that we give while machining, but these allowances result in plays or backlash and stuff. So in case of 3D printers, these even micron level backlashes can cause accuracy or precision issues. So in order to avoid that, we use anti-backlash nuts. Okay, we have been speaking about the frame and the mechanical parts till now. So what in order to move the tool, we need something called a prime mover, or an energy source, or something that results in rotational or translation motion of the mechanical parts. We call them actuators. Uh, Stepper motors are the number one actuator that are used in 3D printers. Since our topic is not related to the electrical stuff, I'll not be speaking about stepper motors, but to give a short description of what stepper motors are, normal 3D motors rotate either in clockwise direction or in anti-clockwise direction. You cannot uh, you cannot stop them in between. Of course, we can stop them in between, but they won't hold the position. For example, if you want to rotate this particular shaft uh, 30-degree clockwise, in case of DC motors, normal DC motors, it's not possible. In case of stepper motors, we can achieve that by stepping, micro stepping those concepts. Using those concepts, we'll be able to achieve 1 degree, 0.5 degree of rotation, all sort of things. 3D printer electronics, we can divide them to 4 main parts: a power supply unit, to drive all the other electronics and actuator steps. A human machine interface, like the name indicates, to interact with the machine. A controller board to control every other electronic and actuator and stuff, and sensor and heating elements to make the machine self-aware and to heat the FDM or fused deposition materials. Okay. This is a human machine interface. This is a display we have. We have a rotary knob for menu selection and a switch to give inputs. A controller board is what drives the entire 3D printer. We need special drivers ICs to operate the stepper motors or the actuators. Uh, uh, CPU, it is usually Atmel chips or STM chips, but whatever be it, this is where the algorithms runs, the codes are there. This particular chip controls everything else, every other motion or every other functions of 3D printer. Then we have MOSFETs. MOSFETs are used to drive high current devices like heating bed or heating cartridges for 3D printer nozzle, etc. We have option here to plug in an SD card and transfer the 3D printer file, the STL file or G code files, not STL, G code files to print. Okay, now sensors. Now think with me. Uh, Machines are dumb. Basically, they are dumb. So if we simply give an instruction for the motor to move to a direction, it will keep on moving and it will damage the motor when it goes to the extreme. So there has to be some sort of a way to let the machine know that these parts or the tooltip has reached an extreme end. So we use sensors, end switch or limit switch. We call them these things end switch or limit switch, so that when the tooltip reaches the switch, it presses against this little flap here, and it triggers a button, and that gives the instruction or gives um, the instruction to uh, uh, the the board to take action accordingly. That is to stop the motor or the motion of the motor. We have heating element called okay. We have heating element here, heaters. Usually they come in 12 volt, 24 volt, and rarely they go up to 48 volts and stuff. And this is uh, a temperature sensor, a thermocouple to measure how much or to accurately control the temperature of nozzle or heated bed. This is a heated bed. It goes from anywhere between 30 degrees Celsius and all the way up to 120, 150 degrees Celsius, depending on the kind of printer that you have. We'll see why a heating bed is required. See, in case of 3D printing, we deposit hot molten plastic, right? When objects are heated, when objects are molten, they expand. And when they are cooled down, they shrink. And when they shrink, a warping occurs. That is, the desired shape was this thing, like it has to be stuck onto the build plate. But if the build plate is not heated, the plastic shrinks and it causes a warping and it detaches the printing material from the bed. So we need a heating bed to maintain the quality of the printing and to avoid warping and other kind of defects. The most important part of a 3D printer is the hot end. This is where all the magic happens. We feed a filament through this PTFE or Teflon lining or guide tube. It goes into the cartridge or the heating portion. This is heat sink. This is where the cartridge is or heating element is inserted. As you can see here, see this cylindrical shape is inserted into this cylindrical hole, and it is fastened. And when it is supplied with the current, it heats up this entire block, and it in turn heats this nozzle. This is a heat break zone. in order to contain, in order to increase the efficiency and contain the entire heat in this particular zone only, we have this heat break, and on the top we have a heat sink to avoid unwanted or undesired melting. Because when we push a filament through the heating cartridge, heating should or the fusing should happen only in this area. Otherwise, if it is heated all the way up to here, we cannot push a molten plastic uh, all the way down. If it is completely molten here, it will clog up the entire system. So we have a heat break here, we have a cooling fan that cools down this portion, and this portion remains usually anywhere between 180 and 230 degrees Celsius, depending on the 250 degrees Celsius, depending on the kind of material that you want to print. Okay, I spoke about pushing the filament to the heating to the hot end, right? There are three main methods by which we push the heating element, filament into the nozzle. One is direct drive, in which the motor or the stepper motor that push a filament is directly attached onto the tool tip or the moving tool tip area. There will be two pulleys, one usually the driver pulley and the other one the driven pulley. The driver pulley pushes the filament downwards, and the motor is usually located near to the heating element or the hot end. Then we have Bowden tube or remote uh, extruder, in which we have a lining, a tube here. It will be attached onto the tool tip and onto the motor, which will be located somewhere remote at a remote location. In the remote location, this motor drives the filament through the tube, and it pushes that filament through the nose. Okay. If you are not, if you have not understood this Bowden tube setup, you can simply think about the accelerator cable or the brake cable that we have in vehicles, right? We have a lining, external lining, a strong, rigid external lining, and the cable moves inside, right? Likewise, the motor pushes the filament through the lining, uh, and it achieves this translation motion. So why direct drive and why a different Bowden tube setup? As you can see, motors are heavy, and if an object is put, if an object is if a heavy object is moving, it has inertia, right? So in case of 3D printer, in previous videos you have seen the tooltip changes its direction rapidly. So accelerations goes very high and can cause damages. So uh, in order to cut down or reduce the mass on the tooltip, we remove the heavy element from the tooltip, the motor, and we place it on a remote location to achieve a low mass tooltip. But the problem is that there are accuracy issues in case of Bowden tube compared to direct drive. So in order to solve the problem, we combine the best of the both and use remote, remote Bowden tube. That is, a motor is placed, the heavy element motor is placed at a different or remote location, but at the same time, it can get the or achieve the advantages of a direct drive. I'll show you a video and you will easily understand by seeing that video. Okay, this is a Bowden tube extruder. As you can see, it is pushed through this tubing, and the filament, it comes out of the tube. See, the motor spins in counterclockwise direction and it pushes against the pulley, and the filament is pushed through the tubing, a PTFE tube. It comes out in the other end. In case of remote direct drive, that is a combination of both, we have a motor that is rotating a rigid cable uh, here. Usually you can correlate it to the odometer cable. Odometer cables are usually a rigid spinning cable attached to the front wheel, and the older one, right, not the digital ones, mechanical ones. So as you can see, it spins the motor and it spins the cable, and that cable drives a gear train on the tooltip, and that tooltip pushes the filament. See, you can see the filament directly goes into the head of the tooltip, and the cable drives a gear train here. So that is how about the remote direct drive works. But the disadvantage is that it is a bit expensive and costly, and the cable that is put inside this red tubing has to be having very high torsional rigidity. Uh, if not, if this particular motor rotates 1 degree here, it has to rotate 1 degree exactly here. If torsional rigidity is less, if it rotates 1 degree here, it might be rotating only 0.5 degree here. So that is not desirable in case of 3D printers. Okay, the next thing is part cooling. Uh, See, this is a long one. The class is a long one, or the presentation is a long one. A lot of topics are being covered. So if you have any kind of doubt, you can simply unmute yourself and ask question. Okay, but I'll be going with the topics. If you have any doubt, you can stop the class, like stop me and ask question by unmuting yourself. Part cooling. Part cooling is extremely important in case of 3D printer because, as you can see, this particular one, it was printed without part cooling fan, and this one was printed with part cooling fan. In case of not having a part cooling, the plastic, the molten plastic doesn't cool down quickly. As a result, when a 3D printer lays the or put down the layer, it remains molten for a longer time, and when more and more plastic come on top of it, it becomes heavy and it sag downwards, compromising the quality. That is where part cooling comes in. It rapidly cools the molten layer that is deposited as soon as the nozzle, or even while the nozzle is printing. So as a result, you have a rigid bottom layer which can support even more molten layers on top. As a result, quality improves. You can see this video here, difference between not having a part cooling fan and having a part cooling fan in case of another 3D printed object. You can see here we have object that is sagged and broken. This is called a part cooling fan. A part cooling fan pushes air towards the nozzle where the printing happens. It helps the nozzle, one thing, nozzle from overheating, and the other thing, main objective, it cools down the depositing the material that is being deposited. So in order to concentrate the air onto the nozzle tip, we use a shroud, or you can simply call them a channel, or something like that. Okay, but it is usually called fan shroud, and it directs all the air to the nozzle tip where the printing happens. So without having a part cooling, we can see here sagging happens. The material oozes down and it does not keep its shape. But in case of having a 3D printing or part cooling fan, you can see we have much higher quality. Yep. See, you can see air being blown towards the middle of the nozzle. You can see a trough here in the water that is created by the blowing air. So this is how part cooling happens. One of the biggest challenges in case of 3D printers is moving material from a 3D printer bed. Usually we use a hard object, a metallic uh, bed or a glass bed, which is very difficult when it comes to removing an item. So we use two different other things. In case of a glass, there are removable glass. It cools down quickly and it helps to remove the object easily. But the problem is that glass is not a very good sticky surface. As a result, 3D printing quality is compromised. But these two things are the hot stuff in the market now: magnetic sheets and spring steel sheets. This is a magnetic sheet. We lift up the entire magnetic sheet. There are magnets. This entire sheet is magnetic and it attaches on to a metallic bed. So when the 3D printing is over, you can simply remove the material, remove the entire bed sheet, lift it up and remove the material. But as you can see, this is not a good solution because since the sheet flexes and bends, it usually causes damage to the sheet, and uh, removing is also a very bit difficult. That is solved by new spring sheet or spring metal uh, removable bed sheets. In this case, the entire sheet lifts up. You can simply flex it, and it easily detaches the 3D printed material. Okay, so what if you don't want to remove the bed or battle with these things? You have continuous printing or conveyor belt 3D printers. In this case, the bed moves infinitely. You can print as many materials as you want, as long, like the advantage is that you can continuously print objects without stopping to remove the object or anything like that. You can even print large objects like see, which cannot be conventionally fit into the 3D printing volume of normal 3D printers. This particular person is printing an entire sword without stopping. Yeah. So that is what conveyor 3D printer is. Uh, I spoke about perpendicularity of the bed and the entire frame, right? So 3D printer has to have perfect perpendicularity between all the planes: the X plane, the Y plane, and the Z plane. It has to be perpendicular. All three has to be perpendicular, exactly perpendicular to each other. So uh, usually when it comes to X and Y and other stuff, it is done from the factory itself. We don't have to worry much about that. But bed leveling is very important. That is, the nozzle has to have the same height from the bed here at this point, at every given point of a bed. If that is not the case, if the nozzle is too high up from the bed, you have this kind of imperfection, and if it is too low, plastic does not get deposited uh, very well. So a perfect printing bed level height is depicted by this portion, a good one. If it is too low, these kind of things happen. This one is good. If it is too high, this problem happens, right? It is not only it's not only related to the height of the way the height of the nozzle from the bed. Sometimes metals, when heated up, warps, bends, and all kind of things happen, right? So the center may bulge out. You might have seen your frying pans in your house where the most heat is exposed to, the frying pan bulges outwards, right? So likewise, there is a chance that the bed might bulge outwards or uh, take different shapes. So in order to mitigate that, we have auto bed leveling. Yep, you can see here the bed is lower here and the bed is higher in this direction. So what it does is the machine checks the height difference and changes or adjusts the algorithms accordingly. Here it is taking the measurements of different points. Let me speed it up a bit. So what it does is, you can see it in a practical case. Yep, he's manually changing the height to demonstrate the thing. See, okay, it is taking measurements at different points. Take a look at this particular rod here, Z direction. Usually, if you are printing in a plane, you don't have to move this Z, move anything in the Z direction, right? But in case there is a difference in Z direction because of the height difference, right? So It is actively moving the carriage up and down. See, it is moving up and down to adjust to the height difference. Yeah, you can see here. It's moving down when it goes to that place and moving up when it goes to this place. Okay, so there are three different types of bed leveling methods, using inductive sensors, using contact sensors, and using strain gauges. In case of inductive sensor, you use okay, this one is a magnetic uh, mesh sensor. Okay, so in case of this, you have magnets embedded onto the sheets, or you usually rely on the magnetics of a metallic bed to measure the inductance and stuff, and create a mesh, 3D mesh of the entire bed and adjust accordingly. Right. It also helps to uh, it also helps to correct the squaredness of the 3D printer. It's looking for the magnet by probing left and right. And once that those points are obtained, it calculates the squaredness of the object. See, a square is there. It checks how it is uh, affecting the 3D printer. And if the 3D printer has a not so good perpendicular build, say for example, the Y and X directions are in an angle, it adjusts the 3D printing accordingly. See, in case of this here, we wanted to print a square and we got an angled rhombus. I'm not sure what to say about that, what the name of that is. But in case of these 3D printers having these kind of algorithms and setup, they actively adjust or uh, make changes to the motion plan and stuff to mitigate the squareness problem. Okay. In case of contact sensors, in the other case, the sensor did not touch the platform. In this case, it touches the platform. It has this thing called BL Touch. It's a company BL Touch, and it takes measurements or height measurements from different points, usually 9 different points. In this case, it might be 16. Because so, anyways, it takes the measurement points and calculates the mesh and creates a mesh and adjusts accordingly. So in a BL Touch, we have a metallic probe, a magnet onto the tip of the metallic probe, and we have a magnetic sensor here, and we also have a solenoid here. So when this particular metallic rod touches onto the build plate and move a little bit high, it gets into the magnetic field of the solenoid and it pulls up the entire rod, and that triggers the magnetic sensor here, saying to the 3D printer board that okay, we have hit the bed, measure the height accordingly. The third kind of thing is a strain gauge or a load cell type. In this case, the entire 3D printing hot end is mounted onto a load cell, and when it is hitting the bed, it triggers a strain change, and it triggers the controller board, and that is how it understands that the printer has hit the bed. Uh, Another problem when we run 3D printers is that the 3D printer run out of filament, but if the printer has no way of understanding or knowing there is no filament in the tube or in the hot end, it will keep on printing because the tooltip is instructed to go in particular paths only. It's not aware of its environments if we are not providing it with good sensors. So that is why we use a filament runout sensor. So this is how a filament runout sensor works. We have a end switch or a limit switch here, And when the filament runs out, it is tensioned in such a way that when the filament or the 1.75 gap diameter filament runs out, the switch is triggered, and it gives a direction to the controller board that filament is run out, you have to pause the print. There are printers with power loss recovery. In case of 3D printer, it has to start from all the way from the beginning, and it has to continuously print to the end. What if power is lost in between? You will have, if there is no way of knowing where we stop printing while the power is lost, we'll have to remove that entire thing, printed thing, and start from the beginning. That is where power loss recovery option helps. It remembers where it lost the power while printing, and it starts from where it has been printed. Multi-material printing. I'm going a bit fast because we have time limitation. We have to cover a lot of topics, but I'll be giving you 10, 15 minutes, 10 minutes at the end to ask questions if you have any. Multi-material printing. Usually the 3D printers are lowest price 3D printers have only single color printing, but we can go wild and print with multiple colors. Here in this case, we have multiple nozzle to print multiple colors, one for black and one for white. There are other setups in which we use only single nozzle, but we use different kind of mechanism to push different kinds of filaments through that single nozzle. See, this particular nozzle prints with black color, and when it's time to print with white color, it moves that particular uh, nozzle moves into the place, right? In multi-material extruders, there are two types of selection, that is filament selector and filament joiner type. In filament selection type, you you feed different filaments onto a filament selector mechanism. You can see 5 colors, and it comes behind at the bottom portion. As you can see here, 5 colors, and there is a selector here. This selector move left and right, rotating and pressing against the filament, so that only filament uh, pressed onto this spinning shaft gets pushed out of the common filament tube or PTFE tube. See, the selector moves, it splices the end of the filament so that a smooth operation can be achieved, smooth motion can be achieved inside the filament tube. There is also filament runout sensor inside this thing. This particular one is coupled with an inductive sensor and the metallic ball. Okay, biggest problem with these kind of things is that you have to use a purge block. This is called a purge block, which is a waste printed portion of the 3D printer, because when you combine, there will be leftover material inside a film 3D printer film nozzle. So we have to completely remove that in order to achieve perfect color. That is why we have to use this thing called purge block. Otherwise, you will get color mix-ups and undesired colors and stuff. Okay. A filament joiner works by fusing multiple colors of filament into a single color filament instead of switching filament, taking it back, switching filament and stuff. In this case, you pre-calculate where exactly the colors will be required, and you fuse those materials, multiple different colors of materials, accordingly using this kind of setup, heating cartridge, pressing it onto becoming filament. As you can see, this particular one is in yellow color, and okay, see, this one is gray in color and this one is blue in color. It fuses the material in this place, and it sends that fused material, see here, gray and blue, it fuses and it sends to the main PTFE tube for printing. Yep, that's it. Now we have tool changer. I spoke about tooltip, right? Tooltips are those things do either addition or subtraction of material from a material block. In tool changer type, you can achieve different types of actions. One is 3D printing, the other one may be CNC milling. This is required because in some cases, in order to achieve perfect surface finish, we'll have to use CNC to remove material extra burrs and materials from the 3D printing object, right? So we use a selector kind of mechanism to print the object and to subtract. For subtraction, this is addition, and for subtraction, we use CNC spindles and stuff. This is another kind of tool changer, which has multiple materials and CNC milling option and stuff. It has a different mechanism compared to the previous video. There are different mechanisms. There is no specific industry standard, but whichever is the best to achieve certain kind of uh, uh, you know uh, goal, we use that. See here, they use the spindle or the CNC setup to mill or create a good surface finish. Okay, this is another setup in which the whole entire 3D tooltips are not mounted onto one thing. Like I've told before, mounting heavy objects onto the tooltip makes it extremely difficult or inefficient because of the high inertia that comes with the high mass, and we'll have to limit the speed of printing, and that affects the entire efficiency. So instead of mounting everything onto single tooltip, you have the option to park tooltips, different types of tooltips in a bay, and you go there, select it, come back, achieve the target, and park it again to switch with different material. See, it goes there, takes the from the parking bay, and right. This is a 3D printer. This is again a different type of 3D printing material. This one is a spindle or CNC spindle. Yeah, high temperature, etc. Like different types of hot ends. Okay, this one has been printed, and they are using a CNC spindle to smooth out the edges and the entire surface. Okay, so far we spoke about 3D printers with 3 degrees of freedom, X, Y, and Z direction, or 3 angles. Now we are going to see 3D printers with more than 3 degrees of freedom, which will help. Like this is, in a sense, we can say that the other one was 2D printing, but in the right sense, 3D printing is this one, because you can see here, it's not limited to the tooltip is not moving in any singular plane, XY plane. It is moving in 3D space. See, instead of moving in XY direction plane, it is moving in a 3D space and printing 3D object in 3D space. Here too, you can see. Okay, so once that is achieved, the one kind of thing is achieved, it is moving onto a different direction and printing in uh, different orientation. If this was to be printed in conventional method, you will have to provide huge supports and spend more and more time printing those supports. But in this case, this is achieved with a great speed. And this one is also another example for 3D printing in 3D space, or in 3D printing in real sense. Yeah. I have only spoken about fused deposition material method of 3D printing. There are other methods called SLA using I'm getting the word. liquid resin printing, and then laser sintering method, which is used to print metals. Since it's a whole different thing, and we don't have a lot of time, I haven't gone into those topics. We have spoken only about fused deposition material or method. So yeah, that's it. Now is the time for you to ask questions if you have any, and you can also give me feedback about my presentation if you have any.
Yeah, actually, this printers which you are shown, is it available with you, or you are taken from various places?
Various
Modeling.
places. 3D printers are costly, very costly. You don't have, we don't have, like, I don't have that kind of money to own every single kind of material, because I
Okay.
took everything from the internet, and I own a 3D printer. It's a Cartesian based 3D printer, which is more than enough for someone like me who is not completely like full time into 3D printing. As a hobby, 3D printing or a 3D printing hobbyist, a simple
Mm.
Cartesian machine is enough to achieve my goals. There are limitations, but it is enough.
Okay, okay. I think most of the machines we are shown is FDM based, right? FDM,
Yes, fused
and the
deposition. Yeah,
hardware is also based on the FDM parts.
yeah, yes, yes.
You are coming across any other machines which are similar, or you have worked on any other type of 3D printing
Yeah,
machines?
actually, my company is located in Kerala Startup Mission. We do have a future lab and a fab lab here, in which
Okay.
different types of materials are there. I'm not sure if there is a laser sintering machine. I think it is there, but three two major things that I have worked on is SLA types of printers and FDM types of printers.
Okay, okay. So SLA printers, is it with you a Fab Lab? It is available.
Yeah, it is available here at Fab Lab. In fact, if you have something, if you have things or projects to work on, you can book a slot for your work earlier
Oh,
using their website, and you can come here and work. There is an option
okay.
for outsiders to work, especially students.
Okay. Yeah, yeah. We have our MTech graduates working on the similar manner,
Yeah.
so we'll be
In
communicating
fact,
on that.
we have other materials, other CNC related stuff like uh, uh, a laser jet, no, not laser jet, water jet, abrasive water jet
What is it?
machining. Yeah. Then six axis. I'm not sure about the degrees of freedom, but there is a CNC machine, and I hope there is a wire ADM also.
Viridium. Okay. It is all these things are in the your Fab Lab
Yeah.
is there.
Yes, Fab Lab it is there.
Okay. Okay.
There is also a laser cutting machine, like for heavy metals and stuff.
Heavy metals. Yeah, yeah,
Yeah.
yeah. So this 3D printing, have you made any commercial products, or like any such works you
Yeah,
have taken?
we used to work in robotics field, like robotics class and kits field. So our kits used to have these 3D printed materials inside the kit. So we sold the we we build those stuffs for our classes and for selling it to others also.
Okay, okay.
Since our volume was very low, we depended on 3D printer. That is no, it is easy. We don't have to invest a lot of money to make the, the injection molds and stuff. So since we didn't have a large volume requirement, we stuck with 3D printing, and that was quite economical. And that is what the use of 3D printers are for: low volume and rapid productions. If you want high volume and extremely fast production, you will have to stick to or change to injection molding or other kind of things.
Okay, okay. Yeah, I think you are passed out in the from 2017, and in the last
Yeah.
4 years, you are in this field. So, where do you think you will be in the another next 5 years? What is your any goal into this
See,
additive manufacturing? Yeah.
uh, okay, hardware. Working on a hardware project has always been, and it still is my dream. But since hardware projects require huge investment and in terms of money and effort, and usually uh, the like return of investment takes more time. we switched our entire focus to software industry, and we currently serve software product for big businesses like Ajmal Bismi, Indus Motors, Kutukaram Popular, Maruti, MyG, etc. So in next 5 years, I'll still be a hobby like 3D printer enthusiast, not an industrialist.
Okay, okay. Yeah, it was until I think the almost all the participants are telling it was a very systematic way of presentation. So it was really informative to many of us who are not into the pure hardware part, because as mechanical engineers, we will be making the products and design, and as well as the fabrication is the area we most of us concentrate in.
Yeah,
So
yeah,
yeah, this was something a different topic, so which introduced us to the various domains and how
mm,
it is controlled, how we can precise, what are the cooling methods, supporting mechanisms, all these things you have interacted. So we are
mm.
very thankful to you for the interactive sessions, and on behalf of the participants and the delegates, once again and thank you. Thank you.